Gibson for the Exascale Computing Project. Today we're in studio at Oak Ridge National Laboratory talking with Stephen Hamilton, an R&D staff member in the Reactor and Nuclear Systems Division at ORNL. He is a principal investigator for ECP's ExaSMR project. Stephen, welcome.
Yeah, thanks, Scott.
Glad to have you. Please tell us, if you will, what ExaSMR is all about.
So ExaSMR is one of the applications projects within ECP that is targeting improving the state-of-the-art for modeling and simulation of nuclear reactors. In particular, we're looking at a class of reactors that are known as small modular reactors, or SMRs. So SMRs have attracted a lot of attention in recent years. And they bear a lot of resemblance to existing commercial reactors, but have the defining characteristic that they're much smaller. So a typical commercial reactor right now might produce more than 1,000 megawatts of electricity, whereas an SMR is targeted more on the order of 50 megawatts. And so the reason why being small is an advantage is from a manufacturing perspective. So a large reactor has many large components that require special facilities to produce, whereas an SMR, by being much smaller, can take advantage of many more manufacturing facilities, and so can have a substantially smaller cost to it.
How do computer simulations improve predictions about the operating behavior of nuclear reactors? And how can ExaSMR advance the state of reactor analysis?
So computer simulation has been a really key component of reactor analysis for decades now. So if we want to study a new reactor design, we can't just go out and build a new nuclear reactor. So it would cost way too much money and take way too long. Instead, what we can do is we can build a computer simulation of that reactor. So we can run simulations that would predict how that reactor would behave if we were to build it. But in order for that process to work, we have to have a lot of confidence that the simulations we're running are actually predictive of how that reactor would operate. And so that's one thing that ExaSMR is looking at tackling. So we want to take the most accurate available numerical methods and apply them to nuclear reactor analysis. So we're looking at what's known as Monte Carlo radiation transport. So first of all, radiation transport refers to computer simulations that describe how neutrons distribute themselves throughout a nuclear reactor, in our case. And so knowing where the neutrons are located and how they're interacting with the materials in the reactor can tell us a lot about how that reactor operates. The Monte Carlo radiation transport in particular is a method that's based on random sampling. So you can think of it as kind of playing a dice game with your reactor. We know that there are different mechanisms, different ways that neutrons can interact. So they might scatter, they might be absorbed, they might cause fission events. And so we model the behavior of individual particles by drawing random numbers, which is a lot like rolling dice. And so as we simulate large numbers of these particle histories, we start to develop a feel for how the reactor actually behaves.
Let's talk about some recent activity. Using Summit, the ExaSMR team discovered that it can not only run its codes on the next generation of supercomputers, but also likely with greater efficiency than on the previous generation. Please give us a few details about this recent success and the benchmarking involved.
Yeah. So this past spring, a number of applications were briefly given access to the Summit computer, which was recently named the world's fastest supercomputer. Mm-hmm. The entire machine wasn't operational, so Summit's still going through an intensive acceptance testing process. So we could only run on part of the machine, which amounted to about 1,000 nodes at the time. So by running on 1,000 nodes, which is about 20% of the final Summit machine, we were able to kind of extrapolate those results out. So we've run our codes on large supercomputers in the past. We have a pretty good idea of how they behave as we increase in scale. So we were able to extrapolate from our calculations to determine what the performance would be if we were to use the entire machine. And then we compared that to previous runs on the Titan supercomputer. And so that's what told us that we think we'll be able to run 30 to 40 times faster on Summit than we were on Titan, which is it's a really exciting number for us because that factor is actually larger than the ratio of the theoretical performance of Summit versus Titan. So that means that not only are we running on Summit, we're actually using it more efficiently than we were the previous generation machines.
Stephen, let's turn our attention to the image we have in the highlight. Will you expound a little bit on what we're seeing in that image, including talking about the colors that we see?
Sure. So this was a simulation of a small modular reactor core that we performed using one of our Monte Carlo radiation transport solvers. So what you're seeing is the total rate at which neutrons are interacting with the materials in the reactor core. So the colors, the dark reds and the hotter colors represent areas where the interaction rate is much higher, and the cooler colors like blue represent locations where the reaction rate is lower. So as you look across the core, you can see variations in the color scheme, which represent differences in the reaction rate due to different fuel enrichments, due to the presence of different absorbing materials. And so looking at these variations of the reaction rate are really important to describing how the reactor behaves.
Okay, so why are those reactions so important? I mean, you're talking about the behavior of the reactor, but in terms of knowing what goes on inside of there, what's so important about that?
So where the neutrons are, and in particular where the neutrons are interacting with the materials, actually causes the fuels to change. So over the course of the lifetime of a reactor, the fuels deplete or evolve over time. So knowing where the reaction rates are the highest tells us the locations where the fuel is evolving the most rapidly.
I see. Okay. As we know, collaboration and integration are a central aspect of ECP. Please share with us a little bit about the nature and dynamics of the collaboration activities that go on within ExaSMR, if you will.
Sure, Scott. So collaboration has been very important to the success that we've had so far in the project. So on ExaSMR, we have collaborators here at Oak Ridge, at Argonne National Laboratory, as well as at MIT and Idaho State University. So we have mathematicians and computer scientists who have great knowledge about algorithms and about how computer architectures behave. And we also have nuclear engineers and reactor physicists that have unparalleled knowledge about how reactors actually operate. So taking all of these people from different backgrounds and sitting down in a room with them together to brainstorm and work through some of your technical challenges is really one of the most exciting and rewarding aspects of being on this project.
Fantastic. That subject dovetails well with what I want to ask you next, and that is your thoughts about the intangible benefits of ECP. It's a huge project. I mean, upwards of 800 researchers across the United States brought together for this purpose of making the leap to exascale computing. So how would you describe that?
So it's really an incredible project, and it's something that is, from my point of view, is unprecedented. So there's been lots of work in high-performance computing over the years, and there's been lots of work in applications development in a variety of different applications. But this is one of the first projects that I've seen that really combines all of these together and says, you know, we have these large computers that are coming down the road, and they're very different than the computers that we're used to running on. And we really need to make sure that our applications projects are able to utilize the machines. So we want to make sure that we're not just running some large stunt calculations, that we're actually improving the quality of the science that we're able to do on these large computers.
ECP really brings it together in a special way. I know there was activities going on, like you said before, but now ECP's brought this together. What is next for ExaSMR?
So a lot of the work that we've done early in the project has focused on development of individual physics codes. We have our Monte Carlo radiation transport solver, and we also have a computational fluid dynamics solver, which describes how fluids flow throughout a system. The next step for us is really taking those two different codes and combining them together so we can run a coupled simulation that, so where the radiation transport describes where the heat is generated, for instance, and the fluid flow, the fluid dynamics describes how that heat is removed from the reactor. So creating that coupled simulation is going to be our next big challenge.
Our thanks to Stephen Hamilton. He's an R&D staff member in the Reactor and Nuclear Systems Division at ORNL, and he's also a principal investigator for the ExaSMR project within ECP. Thank you very much for viewing and for listening.